All right. Hello, class. This is a lesson for AP Physics C. And this lesson is also applicable to IB Physics HL. And I apologize, but IB Physics HL is going to have a second lesson on the Doppler effect later on. But this one should be pretty straightforward. So what we're going to talk about is the first thing we're going to talk about is something called magnetic flux. Okay. And magnetic flux is denoted by the capital Greek letter phi. And the formula for magnetic flux is N B A cosine of theta. So let me tell you about. I don't know what. Hang on a second. I have to mute my computer. So let me tell you about what each of these variables means. So the picture you want to have in your head is you have a loop of wire, and the loop has a certain area passing through the loop. So it's going like this. It's passing through the loop like so. Okay. And the angle that I'm referring to is the angle between the magnetic field and the normal to the loop. So the perpendicular to the loop. So this angle right here is what I mean by theta. Okay. So let me draw you what theta equals 0 degrees would look like. Theta equals 0 degrees would look like, if this is an edge-on view of your loop, then your magnetic field is going like this. Because the normal of the loop points up and down, and the magnetic field also points up and down, so the angle between them is 0. Okay? Theta equals 90 degrees would look something like this. If this is your loop edge on, you have a magnetic field that is running along the loop. So that's theta equals 90 degrees. Okay. At this point, I'm going to check for questions. Whoop, no questions. Okay, so that means I'm doing good. Let me make sure that I'm still live streaming. I'm still live streaming, so that's good too. Okay. So I believe I've explained area, magnetic field, and angle, but what is this number of turns? So if you have a loop of wire, you could have a loop of wire that goes over itself over and over and over and over again. So, if you have 5 loops, that means that the loop of wire goes around once, and it goes around twice, and 3 times, and 4 times, and 5 times, etc. Okay? So it's just the number of times that the wire is wrapped around that area. All right? So now what I would like to talk about is what's called Faraday's Law of Induction. Okay. And let me just write it out, and then I'll explain what it means. So it's all right. So this curly E is called the induced EMF. EMF stands for what's called electromotive force, which basically just means voltage. It's like a battery. So I'm assuming that you were in my class last year, or you were in Mr. Ayer's class last year, and so you know what voltage is. So this says that there's an induced voltage. So an induced voltage means that a voltage just kind of appears without the presence of a battery. So last year when we were talking about circuits, the only time we had a voltage was when there was a battery or there was a power outlet or something like that. This is a voltage that just kind of appears out of nowhere, and it appears whenever there is a changing magnetic flux. Okay, so it's just the derivative of the magnetic flux with respect to time. There's a minus sign here, and we're going to talk about that tomorrow, so don't worry about it for today. So I would like to just do a really simple example. All right. So let's suppose, let me check my questions one more time. I've got to remember to check my questions. You guys don't have any questions for me? All right. How many people are watching? 7 people are watching. Okay. All right. So here's a example for you. So what if we have a wire is looped 8 times around a 3 meter by 4 meter rectangle. Okay. There is a 7 Tesla field perpendicular to the loop. Actually, I'm just going to say there is a magnetic field perpendicular to the loop with, and the magnetic field is changing as time goes on. Okay, the magnetic field is changing. So the magnetic field as a function of time is given by, let's say, 9t cubed minus t to the 4th. So what I want, and that's in Tesla, by the way. And what I want to do is I want to calculate the induced EMF at t equals 1 second. So 1 second in, what is the induced EMF? All right. So I'm going to go ahead and find an equation for the flux. Let me move my page here. So the flux is NBA cosine of theta. So the N, it says the wire is looped 8 times. So that would be N is 8. The magnetic field is given by 9t cubed minus t to the 4th. Okay. The area, it's a rectangle 3 by 4, so that's an area of 12. And it says that the magnetic field is perpendicular to the loop. And so you can see from this drawing right here that perpendicular to the loop means that theta equals 0 degrees. So you have cosine of 0, which is 1. All right, so it looks like we have the flux is given by 96 times 9t cubed minus t to the 4th. Now, I didn't give you units of magnetic flux. I forgot to do that. Well, let's go all the way back here to this part of the piece of paper. And you can see that a flux is a magnetic field times an area. And number of turns and cosine don't have units. So it's simply, so those are unitless. So it's just magnetic field times area. So that means the units of magnetic flux are Tesla meters squared. Okay? So, going back to this example, we have this is measured in Tesla meters squared. Now what I want to do, if I want to get the induced EMF, is I want to do negative the derivative of that. That's Faraday's law of induction. And so doing negative the derivative, I have negative 96 times 27t squared minus 4t cubed. And that would be measured in volts. We want so the induced EMF depends on time. The induced EMF depends on time. And so what I'm going to do is I wanted to know the induced EMF at 1 second, so I'll plug in time equals 1. So the induced EMF evaluated at t equals 1 second is going to be negative 96 times the quantity 27 times 1 squared minus 4 times 1 cubed. So that is negative 96 times 23. That many volts, whatever it is. All right. So Muhammad is asking, what is an instance where you would see an induced voltage? Excellent question. So let's maybe flip this over. Oh, before I flip the page over, notice that in order to create an induced EMF, one of the factors in the equation for magnetic flux has to be changing. If all of these are constant, then when you take the derivative with respect to time, you get 0. So either the angle is changing or the area is changing or the magnetic field is changing. I've never seen an example where the number of loops is changing, so that's going to be constant. But the magnetic field could change, the area could change, or the angle could change. So let's talk about some applications. Let me see if I have any more questions. So some applications. One application would be a radio antenna. And so what a radio antenna is it's basically, or one example of a radio antenna is it could be just a loop of wire, lots of loops, and it goes out like this, okay? And you have a radio wave goes by the antenna. Now a radio wave, as it flies by the antenna, what a radio wave is it's a magnetic field that depends on time and an electric field that depends on time, but it's both of those things. So if the radio wave zips by the antenna, it will create a magnetic field that's changing in time. That changing magnetic field creates a flux that's changing with time. That creates an induced voltage. And then that voltage is amplified, which is then, that's how the radio works. They amplify that signal, they process it, and they turn it into music or communication or whatever. So that's one application of this. You can pick magnetic field is what is changing as time goes on. Another example would be a generator. where what you have is you have a magnetic field, okay? The magnetic field is present, and it's constant. And then you have a loop of wire, okay, like that. And the loop of wire is made to spin at some rate, omega, okay? And so as this thing is spinning, the angle between the loop and the magnetic field is changing. So this is an example of theta changing, okay? Now it's going to take energy to spin this loop, and that energy comes from gasoline. So you burn gasoline, it spins the loop in the magnetic field, and as you're spinning that loop, the angle is changing. You have an induced voltage, which you can then use to power electronics. It doesn't have to be gasoline that's generating that's causing the loop to spin. You could also have, for example, for a wind turbine, it's the wind that makes the loop spin. If it's a hydroelectric dam generating power, it's the water rushing downhill that spins the loop. So you have something that's providing energy to spin the loop, and then Faraday's law of induction converts it into electrical energy. Okay? So I'm going to check the questions one more time. And so tomorrow I think we're going to do some more complicated Faraday's law of induction questions. And that's all I have for today. Have a good night.